Okay, we are recording now. Quickly, we are going to finish up IMU today, the motion tracking primitives with an IMU, and then talk about one application of IMU plus other sensors, a fusion application in localization. Okay. Any questions thus far? As usual, if you can turn on your videos, I'm very happy. But I understand today is time sprang forward, so if you're still in your bed and logging in, I'm happy for that too, actually. Great, let's get started. So we are talking about inertial measurement units, which is an accelerometer, a gyroscope, and a magnetometer. And the problem we said, which could win you the Nobel Prize, is given these inputs, which is accelerometer, gyroscope, and magnetometer, and the initial location of a user, let's say a plane which is on at the Chicago airport, you know the initial location of the plane, and now you need to figure out from the IMU data what trajectory the plane is flying in. We said that one approach is simple as you double integrate acceleration, that gives you displacement. So initial location plus double integration of acceleration should take you to the location of the plane right now. But that does not work. Why? Why does that not work? Someone? We talked about this last class, I think. Yeah. If I just take the initial location and then double integrate the accelerometer, I should be able to get the current location of the plane's coordinate, XYZ coordinates. Why doesn't that work?
Professor, is it due to kind of the noise, and when you double integrate it, it kind of amplifies that noise, and so it'll be off as far as the localization?
Exactly. Okay. So the hardware has noise, and this noise is something that gets added on. And as you integrate that noise, you're essentially integrating the acceleration plus the noise. And the noise gets added up. And then when you double integrate, this noise gets added up even more. And the point is that you have no way of correcting that noise. And one of the analogies for this is the following. Suppose you're blindfolded and I make you stand at a location and I say, walk straight. Okay. You can walk straight, but you are not going to walk precisely at 0 degrees north, right? You are going to maybe bend a little bit here and there, but your brain won't know that, right? So imagine your brain is not able to estimate whether you're exactly walking straight. There is some noise, right? You might be walking epsilon degrees northwest or northeast, but your brain doesn't know that. So over time, these epsilons add up, and your trajectory, if you actually do the experiment on yourself, your trajectory will start diverging from the straight line towards north. The interesting point is your brain would still think you are going straight, right? Because your brain has no way to bring you back, or the brain has no way to estimate how much you have diverged from the true path. Okay? This is essentially the curse of inertial tracking. This is why it's called inertial, because you are always measuring stuff with respect to the previous time point, right? And if you think your previous time point you're walking straight, this time point you'll think you're walking straight, you'll never be able to figure out that I have actually deviated. Okay? So that is one for sure. But what the bigger problem we are saying over here is that even if there is no noise, then can you do it? Right? Your friend in the plane in Chicago is telling you, Anthony, I am getting acceleration in the X direction of 5 meters per second square, in the Y direction of 3 meters per second square. Right? And suppose you take that accelerometer reading and you double integrate, it does not work. Now tell me why it does not work. Anyone else?
Like the reference frame is different?
The reference frame is different. You need to make sure that the plane is pointed towards the north, so that if you know that the plane's nose is pointed towards north, then you know that x-axis, y-axis, z-axis acceleration, what do these accelerations mean in the global coordinate frame on the Chicago airport's map. Otherwise, you do not know. If the plane is in some weird orientation that you do not know, then knowing x, y, and z's acceleration doesn't make any sense, because you do not know how it aligns with the Chicago map or with the Earth's coordinate frame. That's the problem. Okay. So x, y, z, essentially, like we said, this phone, this is the phone, this is x, east is x, north is y, and sky is z. Unless you align the phone with the east-north sky, there's no point. Right? If you double integrate and you add it to the initial location, you will think that the plane is going in some direction. The plane is actually going in some other direction, because you do not know orientation. So this makes orientation necessary. And we said, what is orientation? Orientation is the 3D rotation needed to make the plane's own reference frame aligned with the global reference frame. Okay? So imagine this is the plane's own orientation, own reference frame. Sorry, this is the plane's own reference frame. Means maybe this is x, maybe this is y, and this is z. Right? If the plane's accelerometer is giving you data, the plane's accelerometer will say, how much is this acceleration, which is ax? Sorry, this is ay. The plane accelerometer would report how much is this acceleration, which is ax, and how much is this acceleration, which is az. That doesn't serve you any purpose, right? Because if this is north, if this is east, and this is north, you need to know this theta before you can say how is the plane going in the northeast coordinate frame. And maybe this is up, sky. Okay, so this is called the global coordinate frame, and this is called the local coordinate frame. Make sense? So 3D orientation is the 3D rotation needed to make the plane's local coordinate frame go to global coordinate frame. And we said that rotation is nothing but a matrix. 3D rotation is a 3x3 matrix. So I want a 3x3 matrix which, multiplied with the local coordinate frame, will give me the global coordinate frame. Is that totally clear? So here is the animation where the plane's rotating until the plane's local coordinate frame aligns with the global coordinate frame. Okay? That rotation that you saw, that rotation has to be captured by that 3D matrix, by that 3D rotation matrix, right? The question is, what is that 3D rotation matrix? Okay? If you know the 3D rotation matrix, you're done. Now, if your friend from the plane says, my AX is this much, AY is this much, AZ is this much, what you do, you take that value that your friend is saying, you rotate it to the global coordinate frame, and then you double integrate. Of course, the noise issue is still there, but at least for a noiseless, expensive IMU, no problem. Okay, so good. So now that you understand orientation, hey guys, one quick question, everyone. This is actually key, this rotation, okay? So I have a quick question. Which axis is this rotation happening? can we say, is this the x-axis on which the rotation is happening, y-axis, z-axis, or some other axis? Any thoughts? Okay, it could be any axis, right? It is not that the plane is rotating only around the x-axis, right? The plane could be in some weird angle. The plane could be in some weird angle. Let's say this is the plane. This is the wing of the plane. My thumb is the wing of the plane, right? And this is the global reference frame, right? So the plane might need to rotate in some weird, in some axis, right? So that it aligns with the global coordinate frame, right? So that could be some axis that you do not know. But one thing you know is, suppose that rotation matrix is, let's call it R. That rotation matrix is R. Let's say that axis is X. Can you say something about R and X? Rx means you're taking X and you're applying the rotation matrix on this vector X. What should that be?
Should it just be X, because X is an eigenvector?
Exactly,
Yep.
Exactly. So that should just be X.
Got it.
And that is basically 1x. So one way to think about which axis is the eigenvector of that rotation matrix. So now you have one more meet up with eigenvectors, right? We will figure out what that rotation matrix is, but once you figure out the rotation matrix, you can figure out the axis in which the plane is rotating, and that axis is the eigenvector, because hey, the eigenvector is not changing. A rotation would change everything except the eigenvector. So therefore, the rotation axis is the eigenvector of that matrix, of that 3D rotation matrix. Very good. Good. So now suppose you have the orientation. Suppose we solve the problem. We'll see how to solve the problem, but say you've solved the problem. Now what we need to do is, you have your initial location and you have your IMU in the local coordinate frame. You basically rotate your local IMU readings into the global coordinate frame, right? By using the 3D orientation of the matrix, right? This is basically local to global. Now the output of this orange box is the IMU, same IMU data in the global orientation, in the global coordinate frame, right? You've just done a matrix multiplication. Now you get acceleration, gyroscope, and magnetometer in the global coordinate frame. You take that acceleration, now you double integrate, hope the noise is very small. You get the displacement. This is your displacement. And you know the initial location. You add the displacement to the initial location, you get XYZ. Make sense? Of course, over here you assume noise is negligible / small. Okay. Then the pipeline makes sense to you, I'm hoping. Very good. So the question is, 3D orientation is the key. Oh, you cannot read that very well. But anyway, this says that 3D orientation is the key. So how do you get 3D orientation? Okay. So we've brought down the problem of IMU motion tracking to the problem of 3D or estimating the 3D orientation of the plane. Now, if you ask your friend on the plane, hey, what is your 3D orientation? Your friend has no way of saying initially. Right? How do I know? Okay. But this is where we start to look at how to get 3D orientation from the IMU itself. Okay. Now let's look at it. Okay. So basically the idea is that there are two opportunities to estimate 3D orientation. One is gravity and the second is magnetic north of the Earth. Okay. And the point is, the high level idea is the following. I said, look, IMU can measure gravity, right? So if your phone is like this, which way should gravity be? X, Y, Z, of course, yes, that's true. But which axis will your phone measure the gravity in? This is x-axis, this is y-axis, and this towards me is z-axis. So which axis, what will your phone measure as gravity?
Negative y.
Negative y. Perfect.
Mhm.
So you know, so look at it the other way. If you measure gravity 9.8 meters per second square in your negative y-axis, you can say something about the orientation of the phone. If the phone is in this orientation, you would measure gravity in the negative x-axis. If the phone, by the way, I broke my screen yesterday. If the phone is in the x-axis, then you know the phone's orientation is this. So you can even separate between this and this, right? So does gravity tell you the full orientation? Question to you guys. By knowing gravity, and let's say gravity is on one of the axes, right? Suppose I tell you gravity is on the negative z-axis. Can you say what the phone's orientation is? Suppose I say gravity is on the negative z-axis. So gravity is coming down this way.
I would be inclined to say no, because gravity isn't the only force that's acting on an object.
Correct. So let's say the phone is static. So there's no other force other than the gravity. And the phone is like this. The phone is like this. And gravity now is in the negative z direction, because this is the z direction. So gravity is in the negative z direction. Is the phone's orientation known?
Professor, I still believe that there are some there's different orientations where you can still have it, kind of like still have it be point
all
down.
these orientations, right? All these orientations will have gravity in the negative z direction, right? Similarly, if gravity is in the negative x direction, right? What orientations will have gravity? What orientations will have gravity in the negative x direction? All these orientations, right? So gravity does not tell you the full orientation of the phone, but it helps. Similarly, magnetic north should be pointing towards the North Pole. But in your phone, when you measure magnetic north, if it says that magnetic north is exactly on the x-axis or on the y-axis or some 45 degrees from x and y axis, right? Meaning you see some projection of magnetic north on x and some projection on y. Again, you get some information about what the phone's orientation is. And the high level idea is each of the gravity and magnetic north, they do not tell me all the three unknowns. What are the three unknowns? My orientation, the three unknowns are my three angles with x, y, and z, right? So I do not know the three unknowns, but each of those measurements gives me two equations. So with those four equations, I can basically figure out the three unknowns by over-determining the system, and I will know the orientation of the device. Okay, this is the high-level idea.
I have a question.
Yes.
Does drag play any role for like flying objects in this story?
Flying objects is very interesting. So Adil, can you bring that back once we are done with orientation?
Yeah, sure.
Thanks. Because I don't want to pollute the thinking process right now, but that's very, very interesting. Yeah. Okay. So key idea, what rotation is needed such that gravity is exactly in my downward direction, minus z direction. Okay. And then what rotation is needed such that north is exactly in my frontward direction? Let's say Y or X, doesn't matter. So what I'm going to do is, my phone is measuring gravity, and I'm going to say, rotate the phone until gravity is in the negative Z direction. Right? If I can do that, then I know my phone is like this. It can be anywhere, it can be anything like this, but I know my phone cannot be like that if my gravity is in the negative Z direction. I know the phone is like this or this. So the phone has only 1 degree of freedom left, which is rotating around Z, right? But it cannot rotate any further around X and Y because gravity is only around the negative Z direction. If it was rotating anything around X and Y, I should have seen some gravity along the X and Y direction. Please play with the phone. Please play with your phone at home and make sure you have total clarity. Okay? So that's what I'm going to do. And so this is how I formulate the problem. I'm going to come up with a 3x3 rotation matrix, which multiplied with my local accelerometer data will become 0, 0, minus 9.8. Minus 9.8 is gravity. And what does this say? This says that gravity is in Z direction. You agree? X-axis is 0, y-axis is 0, gravity is in G, and gravity is minus Z. So I'm rotating my local accelerometer data such that gravity comes to minus 9.8. Okay. So whatever orientation your phone is in, this matrix will make sure that the phone comes to some orientation where the phone is flat, where the phone is perpendicular to the horizon, where the phone is parallel to the horizontal. This rotation matrix will make sure of that. I hope you see why. Very good. I have another equation I can do. Okay, so this is what this matrix is doing. Let me do that again. This seems like the phone is rotating along the wing axis, right? But actually, there's also another rotation, right? These two rotations together will make the plane parallel to the ground, right? And this rotation matrix will combine both those rotation along some axis, which is not the wing axis, which is not the tail axis, which is some other axis. But I broke this rotation down into 2 separate rotations, just to give you a visualization. Very good. Now I'm going to do the same thing. Yeah, this determines the tilt of the plane, because now the tilt becomes 0. This is some theta tilt. Now the tilt is 0. So it's parallel to the ground. And that is 2 out of 3 degrees of freedom. Okay. Now I can do the same thing with magnetic north, keeping the gravity in place. So I can say this rotation matrix should not only take gravity to minus Z axis, but should also take the magnetic field, magnetic north, to the Y axis. Right? So now the gravity made your phone flat. Right? Any of these orientations where the tilt is 0, that means the phone is flat. And now you're saying if your phone is in some weird angle, facing some weird angle, that same rotation matrix should make your phone point towards north along the y-axis. Right? So this rotation matrix should serve both these purposes. Okay. And that means your heading and tilt both have been determined. And now you have your orientation. Very good. So the question is gravity plus north enough to get 3D orientation? Okay. Sorry, I may have given out the answer. Is gravity and north enough? Suppose a plane is flying. Is gravity and north enough to get the 3D orientation? Or in other words, where can this idea fail? When will this idea fail where you're using gravity and north as the way to understand orientation? What did I assume while I'm saying that gravity and north is what we need to compute orientation?
Like if you're in an elevator,
Say that again.
your gravity's going to be off.
Sorry, Moise, say that again.
If you're in an elevator,
if I'm in an elevator, what?
your gravity is not going to be like 9.8.
Gravity is not going to be 9.8 anymore. That is true. Make it generalize that even more. Yes, elevator is definitely the case. What else? Someone says something on a chat. The plane is right side up. Okay, that's similar to an elevator. But anything else?
Maybe there's like a magnet affecting the magnetic field.
There's a magnetic field because there is a big server in your environment that will affect. But I want to say simpler things. Any motion, what happens? Suppose some object is moving. Okay.
When it's accelerating.
When it's accelerating, that's right. That's right. Okay. Any real world motion, there will be acceleration, deceleration. Yeah. Yeah, but you're right. Let's say any object accelerating. Right? Remember, right? Even if I move my hand like that, it's very unlikely that the velocity was constant. Right? So these objects are accelerating. What you measure is the vectorial sum of gravity and that motion. Right? But you do not know that you're moving or gravity, right? If I give you a AX, AY, AZ, 3 values, how can you say whether the object is moving or the object is static and only experiencing gravity? Right? So it's not clear that if the object is moving, you can apply gravity equation and figure out, make the tilt of the object 0. It's not clear anymore. Right? Give me an example. First of all, okay, give me an example where if you're moving in a rocket against gravity at exact 1g, right? You're not going to see anything, right? What does that mean? One, that means is your acceleration is against gravity, but you do not know what your orientation is, right? It might be that instead of the rocket going upwards against gravity, it could also be that the rocket is, basically I'm trying to construct a case where the motion of the rocket along all the X, Y, Z directions cancel out because that's the motion, that's the direction in which you're heading. Okay. So maybe you can construct a case at home where you say, oh, there's clearly ambiguity, but the bottom line is there's no way to decouple which one is how much this measurement that I'm getting, how much is from gravity and how much is from the motion of the object. It's not possible. So this is not enough. So you can use this gravity plus north only when the object is static. Actually, I should also mention and magnetic interference from ambience is 0. There are a lot of ferromagnetic materials in the environment. Those create micromagnetic fields, microteslas, but that would affect your north calculation as well. So as long as those are there, you cannot do much. Why? Because any motion of the object will reflect in the accelerometer, thereby polluting the gravity estimate. Right? Because everything will be a vector sum. Right? Essentially, this is your x, y, and z. This is the vector that you're measuring, your ax, ay, az vector. And this ax, ay, az vector is essentially the sum of two vectors. One is gravity and the other is the object's motion. One is gravity and the other is motion. Right? There are many ways to combine the motion and gravity to get ax, ay, az. Make sense? So you cannot do it. Hey guys, one thing you can say is this gravity vector's L2 norm, let's say the gravity vector is G. One thing you can say is the gravity vector's amplitude, magnitude, which is the L2 norm, is equal to how much?
9.8.
9.8.
9.8.
Okay. So the point is that, look, this ax, ay, az, let's call that the vector A. That vector A is your measurement. You want to know which two vectors, one being gravity and the other being the object's motion, made up this vector A vectorially. There's no way of knowing it. There's no way of knowing it despite the fact that the gravity vector G has a norm of 9.8, meaning the gravity vector G has to be in some sphere, has to lie on some sphere where the radius of the sphere is 9.8. But even then, for every point on that sphere, there can be a corresponding motion vector that together will add up and make that A vector, acceleration vector. Right? So even though you can constrain gravity vector to only a sphere, you can still not figure out what the motion of the plane is. Very nice. Okay. So when the object is in motion, estimating orientation or estimating that 3D rotation matrix, very hard. Very good. So what people have done is they have waited for the object to become static. Okay. So here is my question. How do you know that the object is static? There's no good solid answer. There's a heuristic answer. Can you give me a heuristic answer? Roughly, how can you figure out that the object is static? It's not a great algorithm, but it's a heuristic algorithm. What would you do? Suppose I put you at gunpoint and I say, give me an algorithm in the next 2 minutes. Otherwise, I'll shoot you. Okay. What algorithm will you come up with that will say, okay, whether this is the object static or not?
I think I'd die.
Such is the problem, huh? No, you cannot die. You have to give me an answer. Tell me a quick one. Object is static or not?
Acceleration is 0 for many of the axes.
No, but
Or all of the
that means that the object is like this. Right? The object can be like this. In that case, what are you going to say? If this is the orientation of the object, but I tell you the object is static, what should you expect your ax, ay, az to be? What do you expect this value to be?
It should be equal to a magnitude of 9.8.
Exactly.
Yep.
Right? So this is one heuristic where you say, look, is the magnitude of the accelerometer vector 9.8? That doesn't mean that the object is static, right? But it's a reasonable heuristic, right? Because the chances that the object is moving and the accelerometer is exactly 9.8, that chance is small. Okay, so this is a heuristic. This is a heuristic, not a great one, but reasonable, right? Many things have to fall in place for the magnitude to be exactly 9.8, right? In other words, you're saying if this accelerometer vector lies exactly on this sphere, I'm going to say the object is static. Very good. So that's one way. Yeah, question, Eric. Someone? Had a question?
Yeah. How about the gyroscope? Like, does that have to be 0 as well?
Yeah, that's a good point. That's a good point. You can add. Yeah. That's a good point, right? You can say plus gyroscope data should be 0. Right? That's even better. Right? Even then the object can move. Right? You still cannot say that the object is for sure static. Even then the object can move, because the object can move like that. Right? The gyroscope data will not be changing. Right? Because gyroscope only changes with orientation. Right? D theta dt. Right? But more constraints you can add, the better it is. Very good. Right? So now
I had a quick question real quick.
Yeah, go ahead, Adil. Yeah.
Just to clarify, when we say like an object is static, so if it's in free fall, is it static or?
Yeah, if
what
it's in
is it?
free fall, it's not static. In
Okay.
fact, if it's in free fall, the accelerometer won't measure anything. It will be 0.
Okay.
Yeah. So free fall is not static at all.
Okay.
Good. So that was one way of measuring orientation, gravity plus magnetic north. Okay. Here is another way of measuring orientation. Suppose you know the initial orientation somehow from gravity plus magnetic north. Suppose you know that initial one. So you know the initial 3D matrix. Right? Then what you can do is you can single integrate gyroscope. So you know the initial orientation, and then from there on, if the object is changing its orientation, right? All these are orientation changes that I'm showing you. The gyroscope will catch that, because all of these are some rotations around the X, Y, and Z axis, right? If I make the phone like that, or let's say if I make the phone that, right? Look at this change. That will be some rotation around the Y axis and some rotation around the X axis, right? Which will together, it will be some rotation along some other axis, which will capture the two rotations around X and Y axis parallelly together. Okay. So initial orientation plus gyroscope integration will also give me the new orientation. So this is a second way of getting orientation, as long as I know the first one. Right? But why is this good? This is good because I'm not relying on gravity. Right? If the plane is now moving and the plane is changing, or the drone is now changing in motion, you don't care about the drone's motion polluting gravity. All you care about is the drone's gyroscope data, which you're getting from the drone. And if you know the initial orientation of the drone, you can track the drone's orientation all throughout the flight. Right? So that's good, because you're no longer dependent on gravity, so you don't care if gravity is getting polluted. Now, the only issue over here is again that noise. Right? It'll keep, if you do this integration over long durations, that noise will keep adding up. But it's one way. Okay. Good. So gyro drifts meaning over time, the gyroscope, that noise will keep getting added up, and there's no way to reset that noise. so that gyroscope orientation will drift. Okay. So what state-of-the-art sensor fusion does is the following. They say, I would somehow guess when the object is static. I would rely on gravity and north to figure out the 3D rotation matrix during that static time. And then when the object is moving, I'm going to rely on gyroscope. And again, when I figure out that the object is static, I'm again going to go back to gravity and north. And I'm going to keep doing this. Does that make sense? So there are ways to do this in a systematic signal processing way, which says, I have some confidence, I have 90% confidence that the phone is static. And I have 10% confidence that the phone is moving. So I will use the gravity and north with a 90% weight, and I'm going to use the gyroscope with a 10% weight. And as my confidence or my belief changes over time, I'm going to change the weights on these two. Does that make sense? If I'm completely sure I'm static, I'm going to only use gravity and north. If I'm completely sure I'm moving, I'm going to only use gyroscope integration. Right? These are the ways of using your belief as probabilities and accordingly doing your sensor fusion. One technique to do this is called complementary filter. Okay. We are not going to go into the details, but this is the reason why I say signal processing is important in many of these data science IoT applications. And you want to learn algorithms. Python programming you can pick up even on the job and even while wherever you are in industry, grad school, right? But you want to get these foundations in your toolkit early on. Okay? Good. So this allows you to always know 3D orientation. So let's visit the full pipeline now for motion tracking with IMU. Your IMU local coordinate frame data comes in. You first ask, is it static or not? If it is static, yes. Then you use accelerometer and magnetometer data, basically gravity and north, to compute 3D orientation, right? And you then get IMU global. If it is not static, you use the gyroscope plus the initial orientation. We are assuming that the initial orientation is known. Maybe I should say that. Earlier 3D rotation matrix. And that again gives you IMU global, right? Because once you know 3D orientation, you can get IMU global. You put a complementary filter here. Complementary filter. Basically weighted average of two techniques. Right? That gives you IMU global. You take the accelerometer data out of it. You double integrate. You get your displacement. You add to the initial location. You get XYZ. That's the pipeline. And remember, you're doing it at every time snap. Every time step. Every time step, you're saying, what was the previous orientation? What was the previous orientation? What is the current orientation? I compute. So basically, this is important, guys. Let me decline that phone first. Yeah, this is important. Every time step, I first compute my orientation of the device, then I do the integration for that time step. Right? You cannot do the following. Let's say 5 time steps have gone. you know the orientation 5 time steps ago, right? You say, oh, 5 time steps ago, I know the orientation. So I take data for the 5 time steps and I double integrate the acceleration. That you should not do. Because in those 5 time steps, the orientation has kept changing. And your accelerometer data is actually in each of those new orientations, right? So when you double integrate, you want to double integrate that accelerometer at the corresponding orientation. I hope that makes sense. This is time. This is 1, 2, 3, 4, 5. You know the 3D matrix at this point, 3D orientation. Now suppose you take the accelerometer data over here and you double integrate it from time equals 1 to 5. That will be wrong. Because at time 2, the orientation changed and the accelerometer data that you measured at time 2 is in the new orientation in which the object has changed. Time 3, the orientation changed again. So the accelerometer data is in the new orientation again, right? So at time 5, whatever accelerometer you got, that's in the 5th time frame's orientation. So what you have to do is at time 2, you compute the new orientation at time 2, and then use that orientation to double integrate the accelerometer. At time 3, again, you compute the new orientation at time 3, and you use that to double integrate the acceleration, right? Because every time step, the orientation is changing. The object's orientation is changing. So when you integrate, you need to take into account that change. I hope that makes sense. And this is the one that you need to have total clarity on. So if it's bugging you, go back and think. Question?
Yeah, Professor, I had a question as far as like determining like what that amount of time is for each
Right.
time step. Because I was just wondering, like,
right,
for different sensors, they get sampled at different frequencies.
Yeah, basically your answer should be finer the time, the better.
Okay.
Right? Because finer the time, the orientation change will be smaller.
Right.
Right? Exactly.
Okay.
Actually, right, you'll have some errors, right? Remember, your accelerometer is constantly giving you data, right?
Mm-hmm.
So suppose the accelerometer gives you data at time 9 o'clock and then time 10 o'clock.
Mm-hmm.
But between 9 and 10, the object was rotating and the accelerometer was collecting data for all those times, right? And it's going to give you some average at time 10 o'clock, right?
Mm-hmm.
But the average was over different orientations, right?
Right.
And that's the reason why it's getting polluted, right? But if you did 9 o'clock and 9:01 a.m., it's better, right? Because the averaging has happened over a small duration.
Right.
Right. So that's really the key.
Okay.
So finer the time, the better.
Okay.
Right. Okay. So main takeaway, gravity is the main anchor for 3D orientation. If you go down the gravity and north path. But when objects are not static, objects are often not static. And in those kind of situations, when the object is moving for a long duration, right? In these situations, it's a problem. Because if you do gyroscope integration, your gyroscope is going to drift, right? Because t equals 1 to a long duration, right? This is where problems happen. And this is where a self-driving car, planes, this kind of motion tracking with regular cheap IMUs, major problem. Planes may not be too bad. Actually, cars also may not be too bad because the car is big. So you can put multiple gyroscopes, right? So if you turn, right, if the car turns, you can measure these 2 gyroscopes. Or if the plane turns, you can measure these 2 gyroscopes. But if it's a drone, it becomes much worse. And also for drones, because of all those motors and stuff, the magnetic field gets badly affected.
Okay, I have a question.
Yes,
I think this is kind of where I should be bringing up the drag thing.
Right. right.
So let's say you're an object, right? And like you're traveling at a terminal velocity, right? And that terminal velocity, you don't have any acceleration because you're at a terminal velocity, right?
You're at what velocity?
In a terminal velocity.
Terminal velocity. So you're in free fall. Is that what?
Yeah,
it-
yeah.
Yeah.
I'm pretty sure in this case, it's hard to tell. It's hard to track your location because technically, I guess like the accelerometer shouldn't be outputting anything, right?
Exactly. It's very hard.
Okay.
Yeah, it's very hard. But one good thing might be if you're in free fall, right? Then as long as you know the initial position, and if you know that you're in free fall,
Okay, how do you determine if you're in free fall?
how do you determine if you're in free fall? Yeah, there's no way to determine, right? The only thing if you know is that, look, my accelerometer is not measuring anything. Okay. From that, you cannot say you're in free fall because you might be in a rocket which is going exactly vertically upwards with g acceleration, 1g acceleration, right? So there's no way of saying it. But what I'm saying is, if you know you're in free fall somehow, right? Suppose you put an IMU on the International Space Station, and you know you're in free fall, right? In that case, it is possible to measure your location because if it's free fall, it's falling on a very precise trajectory. Do you see what I'm saying, Adil? There's no way to say you're in free fall, period. Okay, because free fall is basically accelerometer value is 0, right? But that could happen for many other cases. Right.
Yeah, this might be like a heuristic thing again.
Yeah, exactly. But what I'm saying is, if you somehow knew you were in free fall, right? This is magically you have that information. Then free fall then becomes an easy case because the free fall's trajectory is very deterministic. Good. Okay. So no good solution today for this case. And on top of this, if you take these cheap IMUs that are in your phones and your watches, they have a lot of noise. And once you double integrate that noise, it's like that blindfolded person, they keep diverging. There's no way to reset. That's basically what gets you the Nobel Prize. Okay. So your job is to solve this problem. No one has a good solution. Robotics communities have looked at this for a long time. They are getting better, but most of the solutions these days are you do fusion with other techniques and you reset, right? So the idea over there is you're blindfolded, but periodically you get to touch something, right? You kind of get to feel something, right? So in my house, if I start walking and suddenly I touch something and I feel the piano, I'll say, I know where I am and I know how much I've deviated. So I should take 5 steps towards my left to be on that same straight line on which I was planning to walk. That's the opportunity. You need to be able to feel something that is ground truth, right? That gives you the opportunity to reset, and you keep, and then you again walk, and then you feel something and you say, I feel my desktop computer. I know where I am. Let me again course correct. That's the opportunity, right? So we will do fusion, and that exactly leads us to the next topic, which is what we call unsupervised localization with this kind of sensor fusion. Okay, questions thus far?
Professor?
Yeah.
You have a noise. Can you expect that to just average out over time? Like, would that mean
that's
0?
a good question. Yeah. So one question is, will the noise not average out over time? Okay, remember one thing. This is a random process. Okay. So one of the, again, this goes into sample functions and so forth. One of them might be averaging out, but over the long run, if you look at how a random walk, the statistics of a random walk, the variance of it diverges over time. Okay? But maybe a simpler way to think about this is the following. When the acceleration is 0, you do not know if the object is static or if the object is moving at a constant velocity. Right? So as a result, when you integrate, maybe the object is moving at a constant velocity, but you will get displacement equals 0. Right? So you are always going to make these mistakes. Now, if you had some motion, if your noise makes it 0, you're going to say that the object is not moving, but actually the object is moving very much, not only constant velocity, but also acceleration. Suppose the acceleration is 0.2 and the noise is negative 0.2. You double integrate. You'll say the object is not moving because integration of 0 will give you first single integration will give you 0. Double integration will also give you 0. You're going to say that the object is not moving. But the object is not only moving with a constant velocity, it's actually even accelerating at 0.2. Your noise made it 0. Right? Later, even if you get another noise which is +2, means the noise is averaging out, that doesn't mean anything because you've already diverged from the first double integration that you've made.
Okay, yeah.
Right? Yeah. Good. Okay, very good. So with that, we'll basically now move forward and move back. We're going to look at an application in localization with IMU, right? With this motion tracking with IMU. Okay, let's dive. And the title of this work, this is a paper. You're going to read this paper and review it. No need to ward drive. Ward driving means no need to train, no need to calibrate like we did in Wi-Fi, right? And this is called unsupervised indoor localization. Okay, so let's look at the localization problem quickly. Where am I in a hotel, mall, office, cruise ship? That's the localization problem. I want to know you are here. That's kind of the problem. We said that, look, GPS does not work because the GPS signals do not penetrate through the ceiling. We said that. We said one possibility is Wi-Fi, where someone goes to different locations and creates this map. This was what we called training or ward driving. And then once we create the map, we look up, we saw how radar does it. We also saw triangulation. All have different kinds of problems, right? There's also things called Bluetooth beacon. This is BLE, Bluetooth low energy, BLE beacons. Basically, the idea is you put beacons at different aisles. So on the cereal aisle, the beacon is going to broadcast Cheerios have a 10% discount today. And if you go past that beacon, you will get that broadcast. So the beacon could also broadcast your location is XYZ. Your location is XYZ. So whenever you get the beacon, and the beacon is like whispering, so it's only audible within a small range around the beacon. And if the beacon whispers your location is XYZ, then if you get the beacon, you know your location is XYZ. Right? So that's another technique. It's kind of a simple idea. But you have to put beacons everywhere in the building. And your hope should be that your beacon's power should be very small so that you do not hear multiple beacons. Your phone does not hear multiple beacons at the same time. Because if your phone hears multiple beacons, you again have a problem because it becomes like Wi-Fi. But then this is also a problem because installation of these beacons and maintenance and changing their batteries, so on and so forth, is a major pain. So the question was, we do not want to rely on infrastructure at all. Can I develop a solution where my phone and only my phone will be able to localize me as I walk around in a shopping mall? Right? So we want a scalable software solution that runs only on my phone and assumes no infrastructure in the environment. Okay? This is where the IMU comes in. Okay? So we also call it infrastructure-less localization. So around 2006, by the way, this is a work which happened in our group, and Samsung actually licensed this technology, and they're looking at whether this is something they can actually bring to real smartphones for localization. I don't know whether I should have said that, but anyway, I said that now. Okay, here is the key idea. Phones have accelerometer, compasses, gyroscope, and now you are walking with the phone in your hand or in your pocket. While you're walking, this is what your accelerometer data looks like. How many of you have never seen an accelerometer data? Have any of you seen an accelerometer data? Guys, can you give me a show of hands in your reactions button if you've not seen accelerometer data?
We saw it as part of our MP1.
You saw as part of your MP1. That's right, exactly. Perfect. So then you know that your phone bounces when you walk, and your phone's accelerometer data looks like this. And then, hey, the peaks of that data are essentially the steps that you count. So that tells you number of steps. Make sense? That's not hard. This is counting peaks.
One of the things that confused me about the accelerometer data that we saw in the MP1, when you were like this scenario specifically, what confused me was like when you're walking up, when you're like, you know, bouncing up and down when you're walking, shouldn't it be centered around 0 and like it should be going above 0 and below 0?
Oh, but gravity is always there, right? So what you're observing is gravity plus the acceleration from that bounce, right? So it's like gravity vector plus your bounce vector.
So
the average of this is not 0, right? Because gravity is 9.8.
Right.
So your bounce signal is always getting added by this 9.8.
A negative 9.8.
Well, that depends on your phone's orientation.
Sure.
Right? If your phone is like this, then yes, negative 9.8. If your phone is like this, then negative 9.8 in the y-axis. Right?
Sure.
If your phone is like this, then it's positive 9.8 in the y-axis. So that depends on your phone's orientation.
But I'm pretty sure in the MP, our orientation wasn't like, you know, like upside down. It was like
right. And that's why, yeah. And that the data that was given to you had the phone orientation in a way that gravity was in the negative, what, z direction? I don't remember now.
Yeah, I don't remember exactly, but
yeah. You see why the average is not going to be 0. If you took the phone to moon, let's say moon has 0 gravity, and there you walked, your measurement will have mean of 0. Perfect. Great. So this is called dead reckoning. So the idea is, oh, by the way, and suppose I'm holding the phone with my y-axis towards north or towards my front. So suppose I can compute my walking direction, right? Suppose I can compute my walking direction. And I can also figure out my stride length. right? What is stride length? How much is, when I walk, what is this length? No, sorry. When I walk, this is my right feet, this is my left feet, and then I take my left feet in front and my right feet stays there. This length is my stride length. Make sense? My left feet is back, and then I move my left feet forward. My left feet is touching the ground, and then I lift my left feet, and I then go and touch the ground again. These 2 points, when my left feet was touching the ground, that's my stride length. Okay. So this, suppose walking direction I can pull out from my magnetometer. Stride length I need to somehow pull out, but there are some heuristics. If given your body weight and your height, there's some heuristics that says this is your stride length. If I can do that, then what I can do is the following. I will say walking direction, stride length, let's call it L. L along the direction theta, I'm going to add up along Li. I'm going to add up I equals 1 to n, where n is the number of steps walked. L theta is basically a vector along the direction theta that I'm walking. L is the length of the vector, the magnitude of the vector. So this vector, I'm going to add up for every step, and that is going to give me my walking trajectory. Right? I didn't tell you how I will get theta. I didn't tell you how I'll get stride length. But for stride length, there is some simple heuristic. For walking direction, let's assume that I'm holding the phone with the y-axis facing my front. Let's assume that. Okay. So this is called dead reckoning, or also often called pedestrian dead reckoning. Where I would walk from my IMU, I will estimate what my trajectory is. This is my IMU estimated path. And obviously it's going to diverge from my true path, right? So the question is, how can I ever do PDR with my IMU and really know that actually this is my location, this is my location, this is my location, and so on? Okay? This is very difficult. This is like the blindfolded man trying to walk and figure out what the walking trajectory is. Now, this is a difficult problem, but it turns out, I forget which year, pilot Charles Lindbergh landed in Paris from New York on his plane without any GPS and used dead reckoning. Right? He looked at the measurements of his IMU or measurements of his plane, and from that he could figure out, like a blindfolded person, what is the right trajectory from New York to Paris. That's very hard, right? Because while you're flying on the Atlantic Ocean at night, you can easily diverge, right? And when he was asked, he said that I actually obtained my fixes from the stars, right? So what I told you as I touch my piano and I touch my computer to kind of figure out how I have deviated, he looked at these stars and he figured out how he has deviated, right? So then, if you want to do this kind of dead reckoning in shopping malls, you need stars in shopping malls, right? Stars in quotes, right? So suppose you have some kind of landmarks or stars in the shopping mall, then what you can do is you can walk, deviate, but once you've deviated and now you know how much you've deviated, you can correct yourself. So once you've encountered this, let's call it a landmark, I mean, for Charles Lindbergh, for a plane, there were stars. For indoor environments, let's call it a landmark. So once you've found a landmark, you correct yourself and you start from the actual correct position again. So this green path basically starts to hug the true path, the actual path, right? This is the idea of how we want to do dead reckoning in indoor environments. But the question is, there are no stars or no landmarks. No landmarks in indoor environments. What are you going to do? Any ideas? Your phone is walking in the, imagine you are inside your phone and you are now moving in a shopping mall. How do you know? Your phone cannot touch a piano. Your phone cannot touch a computer. Your phone cannot see the ceiling. How would your phone know how much I have deviated? Okay, so here's the idea. So actually, when we were doing this project, we were thinking, where are the stars in the environment? There seem to be no stars. This is a random environment, indoor environment. What opportunity do I have?
Oh, maybe
recalibrate.
Could you use like your magnetometer? Maybe, I don't know.
Magnetometer for what?
I don't know. Like in like indoor environments, you might have a lot of like magnetic interference, right? So and like in indoor environments, like I wouldn't say like a human has like a lot of magnetic properties, right? But like
correct.
You know, like that water fountain might have like
correct. Exactly. Okay, exactly. Okay, this water fountain, I don't know what it has inside, but if you look at the magnetic field, if you're coming from here, your magnetic field will be like that, but near the water fountain it will be like, and then again once you walk past it, it will be like that. This is your magnetic fluctuation. Humans won't feel it, but the phone's magnetometer would see this pattern. And it's a repeatable, stable pattern. If you get into the elevator, your accelerometer will be some 9.8, and suddenly there'll be a drop. It turned out, if you come at this spot over here, your 3G signal, which is pretty good, or your 4G signal, which is pretty high, undergoes a weird drop at that location. Because at that location, maybe all the signals from the cell tower undergo a destructive interference. Maybe there's similarly such kind of a spot for Wi-Fi over here. So if you look at the world, so at first we could not see anything, but if you look at the world through the sensors of the phone, you're actually in a matrix, right? Where there are lots of patterns around you. There are lots of stars in the electronic domain. So the phone's goal is somehow to identify these patterns in the environment and use them as landmarks, as stars. Right? So you are really living in a matrix. We just don't know it. Okay. So magnetic fluctuation, pressure change, right? In fact, when you go from one floor to the other floor, the barometer changes. Right? Phones sometimes have barometers in them because they want to do 3D location. So all of these are essentially stars in quotes, or landmarks.
Just as a quick side note,
yes,
for like the pressure thing, wouldn't you have to also know the temperature as well, or?
Yeah, you can change if the temperature changes fast enough, or if there are particular places where the temperature has a stable pattern. Sure, temperature could also be a landmark. Okay, so this is the core idea for unsupervised indoor localization. And the idea is, or three main design questions. Okay, so you understand the core idea, right? Which is reset error using electronic sensor patterns, which are landmarks. Guys, does this completely make sense? Good. I would love to get some more videos. I think Anthony has been the sole person. If you can turn on, great. Otherwise, it's still fine. No problem. Okay. So 3 main design questions. You want to automatically detect these landmarks. No one's going to tell you there's a water fountain here. First of all, water fountain doesn't mean anything. You want that magnetic fluctuation, that pattern. So you need to automatically detect it, 1. You need to localize the landmark. When I'm a blind person walking straight in my house, if I touch the piano, the assumption is that I know exactly where the piano is in my house. If I didn't know where the piano is, there's no point. Right? If I walk blindfolded and I feel and I see, oh, here is my son, that doesn't mean anything to me because my son can move around. And if I feel my son, that doesn't help at all. So I need to localize the landmark. Finally, I need to localize the user. Okay, so these are the main design questions. Okay, great. And the core idea we are going to go after is we are going to basically do a recursive mechanism where I do not know where the water fountain is. I'll make some guess. From that guess, I will guess where I am. From my guess, I will guess the water fountain, and I'm going to keep doing it until I converge. Let's look at it. How to detect landmarks. Okay, good. So let's say you are able to do dead reckoning reasonably. Okay, actually, let's even not forget that. Let's say you start walking inside the shopping mall. This is your walking trajectory. Let me repeat that again. This is your walking trajectory. Oops. Guys, this is something to pay attention to because in the past semesters, a lot of people said that they enjoyed thinking about unlock this technique. So maybe it's a good time to pay attention. Oops. So you walk, and while you're walking, your phone is collecting measurements on your IMU, right? And your phone can roughly do dead reckoning. It's going to diverge, but it still has some dead reckoning estimates. Very good. So now every measurement, you can think of it as your dead reckoning PDR location, which is wrong, right? But it is some estimate. So you get some location estimate and you have the corresponding sensor data from that location. That is what each of these black dots mean. Now, as you walk around, or as many people walk around, every one of them are collecting, each one of them are collecting this data. Every data has a location, a rough location, and the corresponding sensor data. And the sensor data is magnetometer, IMU, Wi-Fi, 4G, everything that you have, barometer, temperature, all data that you have, let's get it. Very good. Now you take this data and you do feature extraction. What is feature extraction? You compute the mean, you compute variance, you compute FFT, different frequency components of your data, you compute standard deviation, you compute skew, you compute all kind of statistical features of that data. And you still have the location. Now, you take these features, let's say you have 100 features, and then in that 100 dimensional space, you cluster those data. You cluster on those features. Does that make sense? What is clustering? Basically, you say what kind of patterns exist in this data that I have gathered. Are you with me? Anthony, you are representing the class today. So is that clear so far?
And I just had a question as far as like the clustering. So you like have all these data points and it's in this 100 dimensional feature space, and then you kind of see how they all kind of, there are areas where they come together, or?
Yeah, you just do k-means. Let's say you do k-means clustering like we did in radar, right? And you have to figure out what k is. But remember, we talked about how to kind of get k.
Right.
And after those, maybe at k equals 20, you get this kind of clusters. And after that, the clustering again goes wrong, or you remember that curve, right? We want to pick at the right k. And at k equals 20, you are happy. And these are the clusters that comes out in k at k equals 20.
Okay.
Right. I'm just showing 3, but there are 20 clusters.
Sure.
Now this is what you do. Remember, each of these points in the cluster has a corresponding location associated to it. Remember, right? Right? Because you're clustering all these feature space, but that point has a location. So this is what you do. You basically project those clusters back onto the physical space. And you check if this cluster in the sensor space also is a cluster in the location space. Does that make sense? Right? So these red points turns out to be close to each other in the location space as well. That means whatever this pattern is, I don't know what that pattern is. That pattern might be something like that. This pattern, which may correspond to this cluster, happens to all come from this location over here. Right? Of course, these locations are rough, so these red points would be scattered. But because your PDR, your dead reckoning is not super bad, hopefully, it's not too scattered. Great. Now you found a landmark. Next, you take the blue points and you again project them back to location space, and you see, oh, there are 2 such location space patterns that you can, location space clusters that you see. That means, you know, this pattern, whatever it might be, happened in 2 locations. You found two landmarks now. But now watch. You take the green points. Sorry, 1 second. Oh, now suppose you take the green points, and the green point goes everywhere. What does that tell you? These green points scatter everywhere. What does that tell you, Eric? Go ahead.
It's just that it's too generic and not too helpful.
It's not too helpful. Can someone guess what that green pattern is? What pattern in the data happens everywhere?
Maybe like step counts or something.
Exactly, it's the walking pattern. Right? The sensor space, when you cluster, that kind of pattern also becomes a cluster, because that's a pattern, right? That goes everywhere. So, you know, this is not a landmark. So this is not a landmark. Okay. So now you've identified these landmarks. And these landmarks could be inertial, magnetic, Wi-Fi, 4G, 5G, anything. Right? So now indoor environments have adequate landmarks. And this is one thing we saw, that even man-made nature, man-made environment and ambience had enough number of landmarks. Okay. So now the question is, we have found the stars, right? So we should be able to navigate. Right? We want to correct our diverging paths once we encounter these landmarks. By the way, one thing to note is that we do not know really what this landmark corresponds to. You cannot say that, oh, this magnetic fluctuation that I saw over here, that is a water fountain. You do not know that. You only know a pattern. In fact, when we were doing this research, we did not know. We in fact saw, oh, there's this magnetic fluctuation and that's a pattern that sticks out. And it's reliably, it's found at this location. And then we said, let's go and find out what is really going on. And then we saw it's actually the water fountain. But from an algorithmic point of view, you don't care why the landmark is coming. As long as the landmark is there and the landmark is stable over time. Okay, good. But look, there's still a problem. There's a catch. We assumed that when you're computing those locations of the landmarks, those locations are pretty good. In reality, the locations will diverge over time. Right? Your PDR will diverge and you're not going to be able to do it correctly. Okay? So we assumed dead reckoning is not too bad. But in reality, it diverges poorly, especially as the person walks around in the shopping mall for 1 hour. After the first 5 minutes, it will become really, really bad. So that means your sensor clusters, when you project it back to the shopping mall, that will be really bad too. What happens then? Right? So here is the idea, okay? And maybe I'll stop at that idea and then I'll come back and pick up on this idea next class. Let's say this is the ideal walking path of a person. So he starts from the origin, he encounters landmark red, then encounters landmark blue, then encounters landmark green. This is what it should be. This is the global truth. Okay. But when one person walks, his PDR diverges this way, and he thinks he has encountered landmark red over here, encountered landmark blue over here, encountered landmark green over here. So observe that the error is growing. Right? Because PDR error will grow over time. So this is the true path. The PDR path. But remember, there are multiple people walking. So imagine another person who walks like this, and this is the path that person takes. This is another person. This is another lady. And this is PDR1, this is PDR2. And this error is different. Because the noise of those sensors are independent, it is entirely believable that if 10 people walk, the landmarks that they estimate, those landmark errors are independent of each other. Do you see that? The noise in the sensors of the 10 individuals are different. Their walking patterns are different, right? Because of all those reasons, these errors should be different. So then what can I do? This is what I can do. I can say that in this 2D space, different people encountered the red landmark at these different locations. And let's assume that the error from the noise is Gaussian. So I can fit a 2D Gaussian model and I can estimate what the mean of that Gaussian distribution is. I can do that, right? I give you a bunch of measurements and I say that, look, these measurements are coming from some Gaussian distribution. What is the mean of that distribution? I can compute that, right? This is a maximum likelihood estimate. And I figure out that, oh, this landmark is actually located here. The mean is over here. So I say that's where the landmark is located. And here is the important part. Please pay attention if you are with me thus far. I say, oh, if the landmark is over here, then I can reset everyone to that location. So all the paths, first of all, these errors are uncorrelated. But then I reset all the guys who walked to that location that I estimated. And the path that started from here, I bring that path to here. And the path that started from here, I bring that path to here. Which means this error, the blue error which was this much, now has become this much. And now I have these blue points. I apply the same thing and I compute the new landmark over here. I reset everyone to that location. Now the green errors have gone down. I compute the new landmark again based on that Gaussian distribution, and I correct everyone's location to that landmark. What am I doing? I am using the crowd's, multiple people's independent errors to correct the landmark, to get a better estimate of the landmark. And once I get a better estimate of the landmark, I get a better estimate of the user's locations. I correct PDR, right? Because I'm correcting the user's locations. Now, once I corrected PDR, I can go back and say, if I have a better PDR, why don't I correct the landmark location again? And then I say, oh, now that I have more different landmark estimates, let me re-estimate the mean of that distribution. I get a new landmark location. I correct PDR. And I keep doing this until no one is improving each other. Right? And that's how I build the landmark map. Right? And now from now on, it's easy. And again, this is where we will stop, but I'll pick up this algorithm, this recursion next class. I am using a bad PDR to estimate landmark, but because multiple people's PDRs have uncorrelated errors, I am getting a better estimate of the landmark. And that one I'll use to correct all the PDRs. Corrected PDRs, better landmark. Corrected landmarks, better PDR. Keep iterating. Everyone's error comes down. The landmark errors come down. The location, the human PDR errors come down. At the point where it converges, I have found the stars. I know the location of the stars. And now I can, any new user who comes to the shopping mall, I will give them the landmark locations. Right? That person will get a map which would say the piano is at this coordinate. The computer is at this coordinate. The dining table is at this coordinate. And I am a blind man. I'm going to start walking. And periodically, once I see that there is a piano, I'm going to walk and I'm going to keep feeling my environment. Once I catch a piano, I say, I think I am here, but actually I'm not. Let me recorrect. And I'll keep doing this. And therefore my error, what will my error look like if this is time? This is the last question I'm asking. This is my location error. what do you think the graph will look like over time for location error for PDR?
I think it'll decrease, but then there'll still be some like DC offset, like when you go towards infinity.
True. But what will it be initially? As I start walking, what will happen?
I think it's going to increase and then decrease.
Correct, exactly,
Okay.
right? And now I meet a landmark, piano, or water fountain. This is going to decrease. It's not going to decrease to 0, right? Because the water fountain localization still has some error, right? It's going to decrease, but that's fine. Again, I will increase. I meet another landmark. I decrease. Again, I increase. Maybe I didn't find a landmark for a long time. And then I found one. I decrease. Then again, I go decrease. The important point is it is not diverging continuously. Okay, good. We will stop there and we'll pick this up next class. We'll start with this. I really want you to look at this flow chart. This is basically the algorithm. Okay, I really want you to have complete clarity, but we'll start with this next class and we'll finish off unsupervised localization and go into maybe hidden Markov models, which is a little bit, again, a little bit math for sensor fusion. Okay, good. We'll stop here. Questions? I'll hang back for any other questions during office hours.
I have one question about unlock. So you showed a picture of a map of like 3 different colored landmarks. After you do the correction based on the multiple recordings of different people walking, do all of these same colored landmarks become unique landmarks, or?
Say that again.
So like you have 2 clusters of blue landmarks here, right? It feels like utility decreases when you have this what is it? This identification of landmarks based on the same color, right? Like if you walk near a blue landmark on the right and you walk near a blue landmark on the left, it's hard to discern which location you would tag that user,
point.
right?
Good point. Okay, but remember, you have rough locations for this blue landmark and rough locations for this blue landmark. You agree, Adil?
Yes.
So if these 2 locations are not too close to each other, then you clearly know that this pattern occurred in 2 different locations.
Oh, okay. So you're including the dead reckoning data plus.
You have that dead reckoning data.
Exactly. Okay.
Exactly.
Okay.
Right. So if these were 2 water fountains, right? And if the separation between the water fountains is larger than your dead reckoning error, you are fine.
Okay. Yeah, that makes sense.
But if this was 2 servers, 2 computer servers in this room, one server over here, another server over here, then your PDR does not have the discrimination ability to figure out that there are 2 landmarks. This will serve out to be one giant landmark, and that's a bad one.
Okay. Yeah, that makes sense. My next question is going to be, it feels like the utility of this system is hampered greatly in like areas where there's a lot of change in like, you know, the environment. For example, like in stores, if you sell a lot of like, items that, are magnetic, right?
Yeah.
Different orientations of those items are going to cause you to recalibrate
Correct.
your system altogether.
Correct. So one thing to do is this data that you've collected. This is the data that you've collected, right?
Yeah.
That data you collect. So for example, for all these Google, Apple phones, right? These companies actually get data. Okay. And for a shopping mall, they would maybe have data for a year, much more, but let's say they've gotten data for 6 months. So when you look at the data for 6 months, you can do this clustering not only in the sensor space, but you can also do it over time. Okay. And maybe you will realize that this blue cluster comes and goes over time. Sometimes it is not there and sometimes it is there.
And you just choose not to use that blue cluster?
Exactly.
Okay.
Right? The question is, if you apply these, if you eliminate these time varying clusters, do you still have enough clusters left that are stable over time?
That seems like, okay, yeah, that makes sense. It just seems like it's a really involved system.
Sure.
Yeah, and it makes sense for like companies like Amazon to do it for like their
Exactly.
yeah.
Exactly. Companies that have data, they can do this, and in fact, they are doing similar stuff. I mean, some of my students have mentioned that there is similarity over there.
Okay.
At Google and Facebook and other places. Now, in fact, one interesting anecdote is the following. When we were running these experiments, we were seeing that there is a nice kind of a pattern that was showing up around noon near a particular cafeteria. And that pattern did not show up at other times. Okay. And then we were like, we put on our detective hat and said, okay, what is going on? And then we realized that during noon, there are queues in the cafeteria, right? And this motion during queues is like you walk 2 steps and you stop. And then again, after a while, you walk 2 steps and you stop, right? This pattern was getting caught, right? And that only happened during noon because that's when the queue was long at the cafeteria. Other times there was that behavior was not there. So we were catching these time varying patterns because of human behavior. And then we realized, oops, we needed to remove those things. I mean, we manually removed those things because we didn't have that much data. But a company like Amazon, Google, Facebook, Apple, they have enough of that data to see these time varying fluctuations.
Okay. My last question is going to be, so I keep getting more questions because of the things you're talking about.
No problem.
What effect, I'm not 100% sure on this. I would guess that humans don't have much of an effect in magnetometers, right? Or do they?
No, what do you mean much effect? Say that question again.
I don't know to what extent humans have effect on like a magnetometer. So you have like a large clustering of people in like a building, right? Does that clustering of people in a building cause any effect on like magnetometers or?
No.
Okay.
Humans have no effect on the magnetometer.
Okay. What about like clustering of phones?
That is below noise floor.
Okay. Okay.
Ferromagnetic materials, big shells, metallic shells, big ferromagnetic materials will have, right? So they will add to the noise. They will cause fluctuations. But remember, the point we are looking for is there has to be a stable pattern of fluctuation at that location.
Okay. I see. Okay.
That is why we are projecting these sensor clusters back to the location space, because we want to see if it is always coming from that location. If it comes from everywhere, you eliminate that cluster.
Got it. All right. Thank you very much.
Thank you very much. Okay. Are there any other questions?
Oh yeah. So are these datas like stored in where are they stored? Like in Wi-Fi access points or something, or?
No. I mean, if Google wants to do this, for instance, right? Google gets data from Android phones, I think 5 minutes a day or something. Okay. And all of that data is stored in their clusters, right? So this whole thing would run on a Google cluster, right? And at the end of this whole operation, what you will have is landmark location and the pattern of that signal, of that landmark at that location. So this will be landmark location 1, pattern 1, landmark location 2, pattern 2, landmark location 3, pattern 3, many, many thousands, n, pattern n. This is the landmark map that Google will create. I'm just giving an example. And then once you have this map, now Google will push this map to every Android OS, or maybe the localization app in Android, let's say.
Mhm.
Right? And now you download a new patch for Android that includes this map. Now you go to the shopping mall, and your Android app knows that, oh, for this shopping mall that you are in, this shopping mall has these n landmarks, and it'll keep looking for those landmarks, for those patterns, right? And once it sees this pattern number 3, it'll say, oh, pattern number 3 corresponds to location XYZ, X3, Y3, Z3, and it'll correct your estimate to X3, Y3, Z3.
Okay, I see. And does like, is this actually implemented like well, or like there's something wrong with this thing?
I mean, you need some engineering still. Conceptually, I think many of the pieces are in place, but then still needs engineering. For example, let's say there is we assume that all the errors are independent, right? But suppose there is some big server room, and that server room biases everyone's magnetometer in the same direction, right? We assume that the crowd, different people who are walking past a landmark, will have independent errors. But if there's a big server room next to that landmark, then everyone's at least magnetometer will get biased in the same way. So there are situations where the independent error assumption may not hold fully. Okay, that's one. And then there are various engineering errors, meaning PDR, different IMUs have different noise patterns, different behaviors. You need to run this across all platforms and do some recalibration. Other problems are I forget what those other problems are. Let me think about them. But yeah, you need a lot of data, right, in order to really run this like a product. So I think, as someone said, big companies can do this, and I think Uber is also interested. Google's already along these lines. But I would say, Eric, that in principle, I think this unsupervised localization serves many of the requirements quite well.
Okay, I see. All right, yeah, that answers my question.
Right.
Oh yeah, just a quick, I guess, quick follow-up. Did you happen to get my email?
I will respond to your email today. Yes.
Okay.
Thanks.
Thank you.
Okay, if there are no other questions, then thank you guys. I'll stop recording now.